So welcome y'all to, we're getting towards the end of this class. So we only have actually today and Wednesday is our last day of new material. And then it's just tests and presentations and more tests and review, and that's it. So this is the big deal. I want to mention the calendar before I get into the quiz, and that is Friday is the exam. So make sure, you get yourself ready. I'd study good 10 hours, practice, 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 practice until you get really good at all these problems. So that's my recommendation. And I want to let you know I finished those videos that I posted. Those give you example problems, lots and lots of them if you like watching videos. And what I recommend doing is click it, see the problem posted, pause, try working it out, and then watch the video to see if you did it right. Okay, and if you can't figure it out, then you watch the video to figure it out. But that's a good way of exploring and figuring out how and practicing problems, because there are, I think, 60 or 70 different example problems, kind of one from each big idea. So just let you know, those are up there. Also, what do we do in a week from today?
Not having class.
Exactly. Relaxing. Relaxing. So a week from today is Thanksgiving week. So I'll let you know next week is completely off. Okay, there's no class, no office hours. I'll probably be checking email here and there, but really we get the week off, so enjoy the week. So that's really important. And then the week after that, very important, I think Wednesday, I believe, is your presentations. So if you don't have partners, post now and be worried. You need to make sure you have partners and you're getting ready for thinking about the presentation. Whenever that is, you need to work on it. Don't work on it, 20 minutes before and think that that's going to be okay. So make sure you prepare for the presentations. And then the week after that will be your final, and it's a Monday final, Monday morning final. So just let you know that that's coming. So that's the whole class. We don't have much left. We're almost done. And then you're done with me. Okay, unless you take third quarter and then you get me again. But you get Bruce next quarter, just let you know. And he's a good guy. Very different style, but he's a good guy. And I know because I get his students the next quarter. And I know that he teaches well and you'll learn from him. So that's the kind of plan, the long-term schedule. So let us get to the quiz. Okay, so here's your quiz. And it's find the following limits or state they do not exist. Show your work. And by the way, at the beginning of the quiz, I put in a calculator. I don't know if you played around with it or liked it or not. What do you guys think? Do you like it better than Proctorio? Huh?
I liked it.
Did everyone else? How about everyone else? Anyone not like it? Because again, I'm new to all this. I've never taught this class online. So Proctorio promised they had a good calculator. I'm not allowed to see it, which is really silly. But one thing I do know how to do is technology. And I'm like, I got another solution. And that is I can embed a calculator into the test itself. And in fact, my guess is I'm the only one at the whole college that knows how to do that, because it literally involves some coding. So it looks like you liked it. I haven't seen anyone said that they like the other one better. So we'll put this one in. Now the other one will still be there to use, but that way I'll make sure this is in for the exam 3 and also for your final exam. So I'll put this one in. And what I'll do is because it does take a lot of space in the test itself, could be distracting. So I'll put it in all the problems that you'll need it for. So anything that I needed a calculator for, okay, or maybe could have needed it. I'm pretty good at doing a lot of arithmetic in my head, but I don't expect you to do like intense arithmetic in your head. Anything like that, every problem will have one. That'll work that way. But I do expect you to know your times tables from 1 to 10. Okay, you should need a calculator to go 7 times 4. Just let you know that. Okay, so I'll put that in. So again, I wanted to test it out today to make sure it worked. Okay, so let's go and do the quiz. And let's do the first one. So what is the first step, by the way, of any limit? Yeah, first step is plug in. Okay, and if you get a knife and answer, you're done. You don't use L'Hopital's rule, you're done. In fact, you're not allowed to use L'Hopital's rule. You can only use L'Hopital's rule on 0 over 0 or infinity over infinity. So if I plug in, then we get cosine of pi. I hope you all know that. You shouldn't need the calculator, although it was there for you in case you needed it. What's cosine of pi? Yeah, -1. So 1 plus -1 is 0. And I hope you all don't need the calculator for 1 minus 1. That's also 0. So we get 0 over 0. And when you get 0 over 0, what does that mean we're allowed to do? So what can you do?
L'Hopital's rule.
Exactly. Okay. And by the way, I do not grade on whether or not you can pronounce it well. I do my best. I actually took French, but one of the many languages I took. So L'Hopital rule is what you use because it is a French guy. And what that says is we can take this limit and instead of looking at f over g, we can do calculus. And I don't think I mentioned this last time, but L'Hopital's rule, when you get 0 over 0, I would say it works at about 95% of the problems, makes it much nicer. And then 5% completely makes it worse. And you got to try something else. I decided not to give you a trick question. But I want to warn you that it does happen sometimes where you use L'Hopital's rule and it's just like, ooh, that's worse than what I started with. But this one won't be. What is the derivative of 1 plus the cosine of pi x? Chain rule.
Isn't it negative sine x?
Yeah, but you got to use a chain rule. So it's negative sine of, and not just x, but it's negative pi times sine of pi x.
Oh.
So it's negative pi. Chain rule is the most important rule of this entire course. So it's negative pi times a sine of pi x. What's the derivative of x minus 1? That is easy. I hope you can all do that in your sleep. So what's the derivative of x minus 1? 1. Okay, what do we do after we have used L'Hopital's rule? What's always the first try?
Plug in 1.
Right, we plug in 1. And if you plug in 1, you get negative pi times sine of pi. What's the sine of pi? Yeah, sine of pi is 0. 0 divided by 1 is 0. And that's our limit. Any questions on that? I guess I should put an equal sign right there. Any questions at all on part A? Easy to watch. Okay. Part B, let's plug in infinity. And I get 1 plus x over infinity. And x over infinity is what? X is any number. What's x over infinity?
Is it just approaching 0 or 0?
Yep. It goes to 0. 1 plus 0 is 1. So we get 1 to the infinity. And 1 to the infinity, you're supposed to know, is one of those, we need to do more work. Okay. And in particular, not quite ready for L'Hopital's rule because 1 to the infinity is not a L'Hopital's rule type. Either you can have 0 over 0 or infinity over infinity. So what we need to do is we need to massage this a little bit. So let's do that. And what I'm going to do is I'm going to call this y because it makes life a little easier. And then I'm going to take a natural log of both sides. And when you take a natural log of a limit, because natural log is a nice function, you can bring it inside. Any questions on that? All right, what can I do with this n as an exponent when I have a natural log? What can I do with it?
Pull it to the front.
Yep, I can pull it to the front. And front of the log, not front of the limit, by the way, because the limit has an n in it, so you can't, oops, put it there. So we can do that, but we're not quite ready yet. We're getting there though. Because then if we plug in, we get infinity times 0. And that's still not okay. So do you remember the trick? When you have an infinity times 0. And again, it was a trick I did 2 days ago, but that doesn't mean everyone remembers it. I'll copy and paste it for now. Yeah, you take that n and write it as 1 over 1 over n. So I'm going to drop this n. And then I think I can do it this way. And that's 1 over n now in the denominator. Okay, and my guess it'll get too busy and small if I do that. So let's try this. Just want to save it in case. Is it readable? Yeah, it's still readable, but let's go to the next line. It's just getting smaller. Okay, so now what I want to do is realize that I now have this guy. And now when I plug in infinity, I get 0 over 0. And with 0 over 0, I can use L'Hopital's rule. So now I got to use L'Hopital's rule. And again, note that the derivative, it's the n that's going to infinity. X is a constant here. It's a little weird, but X is a constant. N is your variable. So we use a chain rule on natural log of 1 plus x over n. The derivative of 1 plus x over n is negative x over n squared, because that's the same as x n to the negative 2. And the derivative, we're looking at n as our variable. So it's going to be negative x over n squared. So let's write that down. And then the derivative of the natural log of something is 1 over that something. And then the derivative of 1 over n is negative 1 over n squared. Anyone lost on the derivatives here? All right, now we can do algebra. So let's do some algebra. I notice I have an x over n squared and a 1 over n squared. In fact, negative x over n squared and a 1 over n squared. So I can cancel the 1 over n squared, the negative 1 over n squared completely. And what I'm left with is just negative x times 1 over 1 plus x over n. See if it lets me do that. I know it negative, just x over n squared times, so it's going to be just x over 1 plus x over n. See if I can get it perfect. There we go. just like that. Any question on the algebra? Okay, what can I do next? Into this nice and easy. What's next? Yeah, plug in. And if you plug in, n goes to infinity, x over infinity is 0, and you just get x over 1, which is x. Okay, I'm not quite done yet, because let's go back and look what we've got. So x was not the limit. That was natural log of the limit. So if I want to get just the limit, what do I do? Yeah, I take e to both sides. So actually I can do it this way and just state the answer now. This is equal to e to the x. Any questions at all on this problem, part B? Part B is very deep. Okay, there's algebra messiness, but it's actually deeper than you think. A lot of times you'll see textbooks define e to the x this way. And then from that, you can get all the other stuff. Okay, but again, it's very important that this is e to the x. Any questions on part B? Okay, let's look at part C. So now we have the limit as x goes to 0 of the tangent of x over e to the x. If you plug in, tangent of 0 is 0. E to the 2 times 0 is? One. Should we use L'Hopital's rule? No, you cannot use L'Hopital's rule. Okay, did anyway is not okay. Okay, L'Hopital's rule works at 0 over 0 and infinity over infinity. Okay, we got 0 over 1, which is just 0 and we're done. Any questions on part C? Okay, you cannot use L'Hopital's rule on part C. Okay, and by the way, if you use L'Hopital's rule and you got 0, then you made 2 mistakes. Because if you use L'Hopital's rule, you wouldn't get 0. You get secant squared of 0 over 2 times e to the 0. 2 times e to the 0 is 2. Secant squared of 0, secant is 1 over the cosine, and that would give you 1, and you get 1/2. Okay, so if you use L'Hopital's rule, you get the wrong answer. Okay, any questions at all on A, B, or C for anything in the quiz?
I have a question. On the homework, it was like C, but they basically just ask you to keep going like twice, and then it ended up being 0, probably because like it didn't exist.
Okay, you cannot use L'Hopital's rule unless you have 0 over 0 or infinity over infinity. So I'd have to look at exactly what you're talking about, but it better not do that.
Okay.
Yeah, so maybe you were mistaken on something, on the plugging in or something. I didn't write the question. I didn't write this homework assignment. Next quarter, a bunch of the problems you get, I wrote, and I wrote all the true falses. But yeah, a few other people. I'm not gonna fib on the person who wrote it if they did it wrong though. But another professor at a different college wrote it, who was working under me. Any questions at all on this quiz? Yeah, so very important. 0 over 0, infinity over infinity, you can use L'Hopital's rule. Otherwise, you cannot use L'Hopital's rule. Okay, very important. Okay, if there's no questions, let's go back.
I mean, I don't know if we can differentiate, but like, how do you know just to stop there? I mean, is it just, we just know that it's 0 and just done, or?
With 0 over 1.
Yeah, I know, but I just felt like in the past, like, yeah, like Alexi said, we kind of just kept pushing through and eventually we found a better way to define it. That's what, like, how do I know that that's the end? Or is it just kind of a thing that you just get used to?
So the rule of limits is if you plug in and you get a number, you're done.
Oh, okay. Yeah, you're right. I
Yeah.
see.
If you plug in and you get a undetermined, like a 0 over 0, a 1 to the infinity, a 0 times infinity, those are all these undetermineds. There's a bunch of undetermineds. Then you're not done. Okay, if you get, let's say 1 over 0, you're done because that's DNE. So you got to get used to what exists, what doesn't exist, and what's still undetermined. Does that make sense?
Yeah, no, I think I get it now.
Yeah. And 0 is definitely a good number. Okay, there's no issues with the number 0. Okay, it's not what you want to get on a test for your percent, correct, but there's no issues on mathematically the number 0. Okay, let's go and let me move to our list of things to do. Okay, so are there any questions about anything else that has come up or is coming up? Hopefully you're all ready for the test on Friday. It's very similar to, I mean, the rules and stuff are the same as the first exam and the second exam. The only new difference is it's going to be an embedded calculator because you wanted it, and I found it. I thought I liked it. It's a Desmos calculator. But otherwise, same rules, Proctorio based and all that. Okay, and same time, all that kind of stuff. Okay, and again, Friday you won't be logging into a Zoom. I won't be on Zoom. I'll be checking email around that time just to make sure no one has issues. But there's no lecture or anything like that for Friday. So kind of real important. Again, we'll talk about it Wednesday. So any questions about anything that's come up, homework or presentations or the tests, or a lot of things coming? Okay, if there's no questions, then what I want to do is imagine you're Newton, okay? Imagine you're Newton, and you want to find out what the square root of 2 is. Okay, Newton was interested in things like that. Do you think he got out his calculator or computer and popped it in, square root of 2? 1.4141. What do you think? Is that what Newton did? Okay, definitely not. Okay, again, I hope you know that he did not have a computer ready to work it out for him. Okay, not okay. So that's not Newton. And I want to let you know, it's going to feel like silly that I'm even explaining doing this now that we have computers. But I want to let you know it's actually a very important thing to be able to do in today's world for several very needed professions. Not because you won't have a computer on your hand. Do you know why you need to be able to do it? You need to be able to figure out how to do it most efficiently. Do you know who has to do it? Things like square root of 2. Nobody knows what profession? Not seeing y'all jump in. Computer programmers. Because they're the ones that have to tell the computer how to make it work. They're not using a computer, they're making the computer. Okay. And yeah, for square root of 2, that's simple. And I'm giving you one that you can all get right away and understand what the square root of 2 is. In the real world, it's a lot more complicated than just square root of 2. But Newton's method is used all the time, and you have to be able to program it to make it work. And I'll let you know, in terms of the real world, it's a lot harder than what I'm going to show you. I'm going to show you Newton's method for a function of one variable, but in the real world, where it's very much needed, is going to be a function of many variables, sometimes thousands of variables for doing this stuff. I won't get into the details, but trust me, I've played with this stuff and known how to do it. All AI stuff needs it. It's absolutely essential. All right, so the one thing Newton knew how to do is draw a picture. Well, first thing, if you want to find the square root of 2 in your Newton, how would you start? How would you start? What would your first step be? Any thoughts?
Maybe start higher than 1, just a little slightly higher than 1, or I mean, probably a little bit more than that, but that's where to start, I guess.
Okay, I'm gonna put your idea there, not the higher than 1 part, but the general idea. So you start. So let's got big. Just a minute. So suppose you wanted to get an approximation for the square root of 2. Okay. Yeah, you know, it might be higher than 1, but I'm going to go simpler than that. Make a first guess. So step 1 is make a first guess. Let's be really easy on ourselves. How about 1, for example? X equals 1. I know you want to go a little higher than 1, but I want to be able to plug in and I want to have no issues with my plugging in. Does that make sense? Usually start with a nice simple guess that's probably pretty close to it. You know that square root of 2 is between 1 and 2, but let's see why. So that's going to be step 2. Step 2 is come up with the equation. Definition of the square root of 2. So what equation is going to kind of define square root of 2? Anyone know? It's very simple, but if you don't think of it, you won't think of it. It won't come to you. Any thoughts? What's the definition of square root of 2? X squared minus 2 equals y. Yeah, but I'm going to say equals 0. Okay, so I'm going to say that x squared minus 2 equals 0. Any questions so far? So there's the equation. And by the way, I'm not writing it down, but for x positive, because remember there's negative roots. There'll be a negative also for that answer. That actually has 2 answers, but we're going to look at the positive solution of x squared minus 2. That definitely gives you square root of 2. Okay. All right, step 3. Draw a picture. All right, and Newton and all of you are able to draw the picture of y equals x squared minus 2. So I'm going to show you, I've done it, or I did it via Desmos. And there's, oops, what do I want? There we go. So there's the picture of y equals x squared minus 2. Y'all good with that? Okay. Now we can look at this and we can say, yeah, there it is. There's the answer. But that doesn't tell us, 5 decimal places of accuracy or anything. But you can eyeball it, right? Sometimes you draw a picture and then make a guess. It actually doesn't matter whether you do step 1 or step 2 first. So then comes Newton. Okay. Now, what was Newton all about? What's Newton famous for? In our class? Many things, but what's he famous for in our class? Calculus, but in our class, dy dx. Okay, and Again, but we're looking at this as a picture. So remember what the picture word. What are the two words? What are the words that you use for dy dx when you're talking about a picture, geometry? Okay, slope, but I'm looking at two words. That's a hint. The slope of what? Yeah, slope of the tangent line. That's better. Yeah, it's the slope of the tangent line. And remember, our first guess was x equals 1. So what I'm going to do is I'm going to go, or what Newton did, is we're going to look on the graph at x equals 1, in this case, y equals -1, and we're going to draw a tangent line. And there's a tangent line. Okay, and this was the next part, which is sometimes called Newton's brilliance, which, by the way, there are a lot of things that were Newton's brilliance because he was one brilliant person. They also, sometimes they'll attribute it to Raphson too. I don't know much about Raphson, but sometimes they'll call this Newton-Raphson method. I'm not a historical expert or anything, but I've heard those words before. So, but Newton's method's easier to say. So then what Newton said is take a look at this and look at this line. And I'm going to say, well, where does the line hit the x-axis? Do you see that? And you'll notice that the tangent line hits the x-axis very close to the square root of 2. Much closer than 1. Do you see that? So then what you're going to do is you're going to come with a second guess. So what we're going to do, let's write this out. Draw a picture, then plot the tangent line at the guess. So we're going to plot the tangent line at the guess. Look at where the tangent line crosses the x-axis. Any questions on that idea? This will be your second guess. Any questions on that? So then if I go and look over here and I see 1.5, that'll be my next guess. So my first guess was 1. My second guess is 1.5, which is a better guess than the first guess. What do you think you're going to do next?
Plot the tangent line at that point.
Exactly. So step 4 is go back to step 2. Go back to step 3. With the prior step 3 guess as the new guess. Start of step 3 is not really guessed, result as the new guess. What do you think the next step is?
Find where that crosses the x-axis.
Yeah, but I'm gonna say it more a better way. Otherwise, they call that hell because you do that and then do that and then do that and then do that and do that, and you never actually finish. Does that make sense? So repeat this process until you have a result at the required accuracy, or give up if necessary. And I'll talk about give up at the end. That's our last thing to do today. So sometimes you're never going to get the required accuracy and you got to give up, but you have to know when to give up. Okay. Now, of course, Newton wasn't thinking this. The way Newton wasn't thinking about what I'm about to say. Newton would do this on a piece of paper and he'd work it out. Nowadays, how do you do this in the real world? In today's world? Any thoughts? I don't see y'all jumping in. So here's how you do it. You program a computer. And program a computer is all about writing a step-by-step process. And you program a computer with the steps in whatever computer language you're using. And then you pop that program into whatever it's needed for, and then people can use it. Okay. And by the way, the person who programs it tends to make a lot of money. So if you're looking for a good lucrative job, this is definitely a lucrative job. Not just programming Newton's method, but programming Newton's method and then designing methods. And kind of that's the whole point of this class. It's not to memorize methods. It's to learn how to design a method to get what you need in an efficient way. And if you're gonna be a programmer, you need to be able to do that. You need to be able to see what is the issue? How do I program it in an efficient way so I get results that are gonna be helpful? And Newton's method, I know Newton was not thinking about programming a computer, but I'm telling you that's how it's used. Okay, and then there's all kinds of modifications of Newton's method, hundreds of them, which you have to decide what's best to program. And that's the real world. Okay, now in this class, we're not real world, but I like to tell you what real world's about because we're just a class. But the real world is you're gonna have to adjust this to make it even better for you. Any questions on this idea? Okay, so that's the process. So I'm not sure, I don't think I've shown you one of these before, but besides teaching math, one of the main things that I like to do that's kind of academic-ish is program computers. So one of the things I did some years back is I actually wrote a Newton's method program. And we can do Newton's method, and I programmed it. Okay, by the way, you think this took me 5 minutes? To program this thing?
6 minutes?
Hours. Hours. I want to give you a reality check. This doesn't just happen. Okay, there are a lot of lines of code on this thing. Okay, so you can put any equation you want. Okay, and by the way, reading equations is not easy with a computer. You put any equation you want. So let's just do the one we just did. X squared minus x squared minus 2. Okay. And what it's going to do is it's going to show you Newton's method. Our first guess is 1. And for now, we'll leave it as it is. It was a lot of work to try and get all this zoom in and zoom out and changing the width and height and all kinds of stuff. And I hit submit. And this is Newton's method being applied 6 times. Okay, so the 0th guess is 1. The first guess is, or first iteration, sometimes I call that, is 1.5. Okay, and by the way, you probably know square root of 2 a little bit. The second guess is already 1.41. The third guess is 1.414257. We're already good to multiple decimals of accuracy. The fourth guess, 1.41421336. And the fifth guess is the same as the fourth, which means we're done. If we wanted 7 decimal places of accuracy, we got there in just 4 guesses. Okay, 4 iterations of Newton method, and we're there to 7 decimal places. Okay, and that's pretty darn accurate. That's more accurate than just about anything you'll ever need in life. Does it sound right? Now, what I'm going to do is I'm going to zoom in a bit. And let's take a look at watch it happen. So there's our first guess, our second guess, our third guess. And already you need to zoom in more. You can't even see anything. But do you see that? So the first guess, or the 0th guess was 1. We take our tangent line, and we get to right about there, which is 1.5. And then we take that value of x, put it onto the graph, and then find the tangent line at that point, and that'll point almost right at the root. Okay, in terms of our eyes, at least my eyes, already on the 3rd iteration of Newton's method, I can't, that's it, I'm done. Any questions on this big process? Any questions on Newton's method and what it looks like as a picture? Not too bad. Okay, and again, Newton did this hundreds and hundreds of years ago, so obviously there's nothing too complex involved. Okay, it involves calculus, and we can do it and we can understand it. All right, so let's go back. And now that we have at least a pictorial idea, now let's see if we can come up with doing Newton's method without drawing pictures. Okay, in other words, we're going to look at these steps now. We got our first guess. We got to come up with the equation of the definition. That will be given to you, or you'll got to figure it out. Sometimes you got to come up with an equation because you want to find a critical point. So you take a derivative, set it equals 0. But Newton's method, you got to have something set equals 0. Okay, then the draw the picture, we're not going to do. We're not going to plot a tangent line. What we're going to do is find the equation of the tangent line. So that is the key to Newton's method, is find the equation of the tangent line. So who remembers? What's the slope of the tangent line? What's the slope? You better all know what the slope of the tangent line is. Okay, and when I say the tangent line, I don't mean for our example, for in general. Yeah, it's a derivative, okay? Again, it is Newton's method, and Newton was all about the derivative. So what we can say is the slope of the tangent line, and just because we're used to it, I'm going to call it m. M is equal to f prime of our guess, okay? And I'm going to call the guess that we're on x sub n. So if you're on the 4th guess, we're talking about f prime of x sub 4. And each time, each iteration, you're going to have a different x sub n. Any questions on that? Okay, to find the equation of a line, we need the slope. What else do you need? We need a point. But the point we have, so the point is x sub n, comma, f of x sub n. Because y equals f of x, right? Any questions? Have I done anything fancy yet? Okay, now let me ask you something, and you're all required to know this. Is you're given a slope and a point. How do you get the equation of the line? Poinsot form, in particular, what is that? You should all remember? Yeah, it's y minus. Now our y1 is f of xn. right? So y coordinate of the point is equal to m, which is f prime of xn, times x minus x sub n. Any questions on the equation of the tangent line? It's all in general. We haven't even really used Newton's method yet. What we're doing is we're just getting ready. So far, so good? Okay, now I want to go back to the picture again, because you might have already forgotten. So we had this picture, and the idea is our first guess was here. We looked at the tangent line, and then where is the next guess? How do you get the next guess, visually at least? So here was our first guess. And visually, how do you get the next guess in some words? Yeah, we look at the x-intercept of the tangent line. So the next guess will be the x-intercept of the tangent line. It's going to be the x-intercept of the tangent line. Well, by definition, how do you get the x-intercept of the line? If equation-wise, not picture. What does it mean to be the x-intercept in terms of our equation? We know a number. Which of these do we know? Yeah, y equals 0. So what I can do is I can take my equation and I can put in y equals 0. Is that clear? All right. And I want x. So guess what? I do some algebra. So what I'm going to do is 0 minus f of xn is a negative f of xn. I'm going to divide by f prime of xn. And what I get is negative, oops, let's go this guy. There we go. So we get negative f of xn over f prime of xn is equal to x minus xn. I want x. So easy step, what do I do? If I want x, this is not hard. Yeah, basic algebra. So what do I do? So what algebra goes? Yeah, we add xn to both sides. And I'm going to switch around. I'm going to put the left on the right and the right on the left, just because it looks better. And I can say that x is, and now I'm not going to call it x anymore, because it's our next guess. So I'm going to say xn plus 1 is equal to x sub n minus f of x sub n over f prime of x sub n. And then the next thing I'm going to do, I can make it really big and put it in red. Do y'all know why I did that?
Because it's a theorem, maybe?
Yep. This is the theorem. It's the theorem of the day. This is the Newton's outside the equation though. Newton's method equation. Okay, so whenever you need Newton's method, this is how you do it. Is you take your first guess, then you take your first guess and you plug it into F, you plug it into F prime, and then you find your guess minus F over F prime, and that's your next guess. Any questions on this idea? All right, let's do our example just for fun. Let's find the square root of 2. By the way, does this give you the exact answer when we're done? Does this give you the exact answer, the root? Yeah, not exact. Okay, usually pretty close. So let's do the square root of 2. So let's do the example. So let's go x squared minus 2 equals 0. And let's say that x naught equals 1. Any questions on that so far? So that's the question. And the question is find the square root of 2 to, I don't know, maybe 4 decimal places or something like that. And then we'll see. So find the positive solution or the solution accurate to 4 decimal places. My guess, maybe I'm wrong, is that none of you know the square root of 2 by heart to 4 decimal places. Am I right? Maybe I'm wrong. Maybe you guys, someone knows 100 decimal places for all I know. But I know for sure, I can guarantee that none of you knows all the decimal places of square root of 2. Okay. And if you do think you know, then you're wrong. Okay. You can't know. Okay. But what we can do is get as many as we want. All right, so let's go through, and I'm going to first just write down the equation. Typically, just because it's easier to type and to write on paper too, if you can do it, is I tend not to use the subscript notation. I'm just going to use a y notation instead. It's just less writing. So I'm going to say y is equal to x minus, and then it's going to be f of x, and f of x is x squared minus 2, over f prime of x, and f prime of x is 2x. Any questions so far? Any questions on how I came up with the Newton's method equation? And again, it's just a lot easier typing if I don't have to do subscripts, if I just call it x and y. All right, the next thing I'm going to do, because for organizational reasons, it's so much easier, and I'm going to make it a table. And let's see how many I need. Need f, x, f, f prime. I think that's good. I'll just do a bunch of rows. We won't need all the rows, but we'll need some. Okay, so what we're going to have in our table is we're going to have x. We're going to have f of x. We're going to have f prime of x. And then we're going to have x minus f over f prime. Any questions on the table? Okay, what's the first x? Not a trick question. What's the first x? Yeah, it's 1, because that's our first guess. Well, what's f of 1? Right, 1 squared minus 2?
No, 1.5.
No.
Oh, no, I'm sorry. That was the whole answer. It's 1.
-1. Yeah, we'll get to the 1.5, but that's not f of x. Okay, what's f prime of x? That's 2x, by the way. So you might want to write down in our example, f of x, because some of you are having trouble with this, f of x is equal to x squared minus 2. And f prime of x equals 2x. So what is f prime of 1? Is 2. So now we plug in, we're going to have a 1 minus -1 over 2. What's 1 minus -1 over 2? Let's go by decimals. Yeah, 1.5. All right, so now our next x is 1.5. So we always take this last number, the x minus f of x over f prime of x, and that gives you the first number for the next line. Okay, and that's called recursive. That's called recursive algorithms. Is what comes out is what comes in into the next step. And that's called recursive. So now we do f of x. Again, f of x is x squared minus 2. 1.5 squared is 2.25. 2.25 minus 2 is 0.25. Any questions on that? F prime of x. Again, f prime is 2x. 2 times 1.5 is 3. Any questions on that? All right, now it gets a little harder in my head at least, but I could do it. So now we're going to go 1.5 minus 3 minus 0.25 over 3. Okay, maybe I'll pop that in a calculator. 1.41 and a bunch of 6s with a 7 at the end.
Larry, if we're not using like a computer or calculator, or are we, like, should we just turn those into fractions?
Remember, you're gonna, on a test, I told you, I even showed you, you're gonna have a calculator on you.
Okay, I was just wondering at what point we're Newton and what point we're in the future, you know? But,
yeah.
Okay, cool.
Because remember, the point of this, I know this sounds a little weird. The point is not to get an approximation of the square root of 2. What's the true point of what we're doing?
Getting the square root of 2.
No.
No?
No. Okay, come on, you use a calculator to square root of 2. What you're doing is you're learning how to process and create algorithms. That's what you're learning. And if you can process and create algorithms, then you'll have a good job. Does that make sense? And a good career. Okay, so keep in mind that the whole purpose of calculus is not to get an approximation of square root of 2. It's to be able to come up with a problem that is sent to you and figuring out how to solve it. That's what you're getting at. And the reason why you're required to have calculus in STEM majors is not so that you can use calculus. It's so that you can come up with some step-by-step, sometimes rough solutions to problems. Because if you can do that, then you'll be a great engineer or a great doctor or a great computer programmer. Does that make sense?
Yeah, absolutely.
That's the purpose of this class. It's not to get the square root of 2. Okay, no one really cares about that. Okay, but it's to understand processes. Okay, or a very good chemist. I'm going to put it that way. Okay, so again, you're going to have a computer, but you may have to program the computer. Okay, And this is just first year. This is freshman level. Okay. When you become an engineer, that means you finish senior level or a chemist or whatever. So definitely you have a lot more to do. Okay. So now, by the way, we want 4 decimal places. So I have 1.4167. That's why I kept 4 decimal places. Then I put in 1.4167. And then we say, what is f of x? Well, f of x is 1.4167 squared minus 2. Which is 0.4982. Then we say, what's f prime of x? Well, f prime is 2x. So that one I could do without my calculator, I believe. And that is 2.8334. Any questions on that? Okay, then we take x minus f over f prime. So that's going to be, now I got to, trying to remember, it's hard enough. I won't remember the last one. So I'm going to copy that one, see if that works. So 1.4167 minus 0.4982. Divided by 2.8334. I'm a little worried about it. I think I made a mistake somewhere because it shouldn't be far from what we got. Let me double check. So we have 2x, 2 times 1.4167. $2.8334. That's right. And then we should have x minus f over f prime. So it's 1.4167 minus 0.4982. Divided by, one more try, 2.8334. 2.8334. And I get 1.2409. I have a 1. Did I miss something somewhere? Got all kinds of answers.
I don't know if this is right, but I got for x of the answer to be 0.0069, or the function of x.
That doesn't sound right. Because 0.4982 over 0.28334 is a small number.
For that one, I got 0.00245.
Right. And if you go 1.4167 minus 0.00 something, you get something really close. You get 1.4 something.
Right. Yeah. So I'm saying, I think you have the function of 17 over 12 to be wrong. I think you had it at a higher number. You have it at 0.49.
Which number do you think's wrong? This one
right here?
Yeah, Larry. That's.
Oh, yeah. That is, let's see, f of x. There we go. X squared minus 2. Yeah, that's the mistake, Polly. So let's try again. So here's my x. There's definitely a mistake somewhere. It's really hard to go back and forth on screens, which you'd never want to do. So we're going to do that, and we're going to square it, and then we're going to subtract 2. Oops, what just happened? Let's try again. Square minus 2. That's better. I knew there was something wrong. 0.0070. And this is 1.4167. Much better. And then F prime 2883. And now let's plug in. And hopefully it'll work now. 1.4167 minus 007 over 28334. Interesting. 007 just died last week, I believe. The first 007. So 14167. And then minus 007. Divided by 2.8334. And you get 1.4142. Okay, so now we go 1.4142. And now f of x, let's get this right this time, x squared minus 2. And the good news is to 4 decimal places, that's 0. Any questions on that? Why do I know I'm done?
Because you're going to divide into 0?
No, I'm done because that's what I want. I want f of x to be 0. Do you see how it works? So to 4 decimal places, f of x is 0. And that's my goal, was to find where f of x is 0. So the answer is 1.4142. And that will give me 0 to 4 decimal places of accuracy when I plug in. Any questions on using Newton's method? Any questions? Okay, let's do something weird. I'm going to do a different guess. I'm going to kill this guy. What if instead, let's say we were naive, and 1 is nice, but what's the easiest number to plug in into most functions? Easier than 1. 0. So what if your first guess is 0? So if your first guess is 0, then we're over at the 0, negative 2. And the equation of the tangent line there is y equals negative 2. What's the next guess? So what's your next guess? Yeah, you're stuck. There's no next guess. Because again, the Newton's method is you draw the tangent line, and then you see where the tangent line hits or crosses the x-axis, and that's your next guess. Well, guess what? This one didn't work. Okay, this one didn't work because if we look at the tangent line's horizontal. This doesn't cross the x-axis. So Newton's method fails, is what we say. Any questions on this idea? Any questions? Okay, so now let's talk about failure of Newton's method. So one case is if you have a horizontal tangent line, you're screwed. Okay, and by the way, horizontal tangent line, that means that if you do your calculation and f prime of any xn, anywhere along the line, could be x2, x10, whatever, if you ever get an f prime equals 0, then Newton's method failed. Any questions on that idea? Okay, so Newton's method does not always work, okay, which is a problem, by the way. Okay, let me give you another obvious one where Newton's method fails. Let's suppose, let me draw a picture. Let's suppose instead of x squared minus 2 equals 0, let's suppose you had x squared plus 1 equal, and you want to set that equal to 0. What's your first guess? I'll let you choose. Okay, you could choose 1. What's going to happen? Well, if you choose 1, it's going to cross over here somewhere. And then you go over here. And then you're going to choose this one. It's going to cross over here somewhere. Then you're over here. Are you ever going to get where f of x equals 0? Okay, it's a stupid question. Why is it a stupid question for this example? Can you think of a better method than Newton's method to find where this crosses 0? To 4 decimal places, let's say? Right, it doesn't cross 0. So of course, Newton's method is going to fail if there's no solution. Okay, so that's number 2. If there is no solution, then of course Newton's method will not find the solution if there is no solution. Okay, but you'll sit there all day long trying. What's going to happen if you have a computer program and you run the computer program with Newton's method and you choose any guess? Any ideas? Okay, it's going to spin all day long and end up with nothing. Okay, it's just going to go and go and go, and yeah, make some coffee. Exactly. It's going to have a spinning wheel, and it's just never going to finish. So as a programmer, by the way, if you do Newton's method, in fact, let me show you what I did. This is your typical thing you want to do. Let's make it a +1. And if I submit, okay, look what just happened. Fail. Okay, so I programmed it, so I detected that Newton's method was going to fail, and then I just gave the message fail. So if you're a computer programmer, that's what you want to do. You want to do something like that. You don't want to let it spin because that annoys everyone. It's better to have a message that says fail or whatever you want to do, okay, than a spinning thing. Okay, you don't want a computer to crash. Okay, so you could have no solution and that could happen. Okay, but let me show you another thing that could happen. Let's do mine now. Let's zoom standard. Let's just go that way. It's the easiest. Let's suppose you have y equals x cubed. Okay, now I hope you all know what the solution is to y equals x cubed. I think this one works. If not, it's a different one. Let's say my initial guess is 1. Okay, so this one seems to work. On the other hand, instead of x cubed, what if we did x to the 1/3? And let's try that guy. Okay, it's got all kinds of problems. It turns out, and I think I programmed it so it can't handle x to the 1/3, but that's okay. Wonder if I make it 2/3, if it'll like it better. Let's try that. Nope, didn't like that. Yeah, I think I programmed it. I think it's got problems with what I used. So the idea is what's going to happen, you're going to oscillate. You can go back and forth and back and forth and back and forth. So if we look at x to the 1/3, and let's see what happens if you use Newton's method. Let's say you choose 1 as your first try. Okay. So if you choose 1 as your first try, then let's see what happens. Well, if you have 1 as your first try, then the equation of the tangent line, it goes through 1, 1, right? It has slope 1/3. So it's going to be 1/3 times x. And then it goes through 1, 1. So if I plug in 1, I'm supposed to get 1. So it's 1/3x plus 2/3, I believe. Is that right? Yeah. And let's zoom out a bit. And then our next guess is 8. Is that a better guess than our first guess? What do you think? If x equals 8, have we done better? Are we getting better? We started at 1. Now we're at -8. The answer is 0. I mean, obviously 0 to the 1/3 is 0. That works. And then if we're at 8, and we draw that tangent line is almost horizontal. It's not quite, but it's going to go way the hell out there. You're going to be way out to the right. And then if we do it again, it's going to be even more horizontal. And you're going to be even farther in. Does that make sense? So what can happen is that you can use Newton's method, and instead of reaching the answer, getting closer and closer, it actually gets farther and farther. And that can make, and Newton's method could fail that way too. So the answers, so the iterations get farther from each other. Instead of closer. And that can happen. The issue, by the way, was y equals x to the 1/3 has a vertical tangent line. There's issues there. It's not differentiable even. Okay, so there's reasons why Newton's method can fail. Again, you can have a horizontal tangent line. You can have no solution. It can get farther from each other. It can even go back and forth and never reach. It can go 1, -1, 1, -1, and neither of those are roots, and it just goes back and forth. Okay, or it can go back and forth. So as soon as you get back to one of your prior guesses, it's over. Newton's method failed. So there's lots of reasons Newton's method can fail. So I'm not going to get into the details of this because we have no minutes. But what you do is that if you're worried about Newton's method failing, you try Newton's method on maybe 50 guesses. And remember, use a computer, and computers are pretty fast. And then you choose the guess that works, and you hope one works. So that's kind of how you would program a computer to do it right. Okay, and if none of them work, then you go for fail. So we're out of time. Let me stop the share and stop the recording.